Hello students, see in the last lecture we have completed the half chapter, that is the structure of atom. So in this lecture we are going to complete a very important topic from that, to how to write the electronic configuration, what are the rules related to write the electronic configuration. So we start with the remaining topic of the structure of atom. See, in the last lecture, we also completed the shapes of orbital and the Bohr's theory, Lemon series about the hydrogen atom. So, today we'll see the energies of orbitals. The energy of an electron in the hydrogen atom or hydrogen like species is determined by the principal quantum number alone, because only interaction in this species is attraction between the electron and nucleus. An increasing order of energies of orbitals in the hydrogen atom is given by 1s is having the less energy, then 2s is equal to 2p, they are having the both same energy. Then 3s, 3p and 3d are having the same energy. Then 4s, 4p, 4d are having the 4f having the same energy. According the electrons are filling in each shell. Of course, the shapes of the concerned sp-df orbitals are different as described earlier. The orbitals with same energy and the corresponding wave functions being different are called the degenerate orbits. So, energies of an electron in a hydrogen atom is determined by only the principal quantum number, that is the n. Thus, in hydrogen atom, 2s and 2p are degenerate orbitals. In multi-electron atoms means atoms having many electrons, there is a mutual repulsion among the electrons. The energy of an electron in multi-electron atom therefore depends both on principal quantum number n and azimuthal quantum number L. See, in hydrogen there are only one electron. So there is only principal quantum number is useful for write the electronic configuration. So principal quantum number is very important in case of hydrogen. But in multi-electron atoms, both principal quantum number as well as azimuthal quantum number L are required or are important to write the electronic configuration. The lower the sum for an orbital, lower is its energy. Sum n plus L you have to calculate, and if it is the low, then the lower is the energy of that particular orbit. If two orbits have the same n plus L values, then orbitals with lower value of n is of lower energy. This is called the n plus L rule. See, what is this n plus L rule? See again. Lower the sum of an orbital, lower is its energy. And if the two orbitals are having same n plus L value, then you have to see the value of principal quantum number. If the n is having the less value, then that orbital is having the less energy. This is the n plus L rule. From the n plus L rule, the increasing order of energy of orbitals in multi-electron atom can be written as 1s less than 2s less than 2p less than 3s less than 3p less than 4s, 3d, 4p, 5s, 4d, 5p, 6s, 4f, 5d, 6p, 7s. See, this order of filling the electrons in each orbit you have to remember, and according the electrons are filled in each shell, and you have to write the electronic configuration according to that. In multi-electron atom, electrons occupy different orbits. See, if the electron is having the less, if in an atom electrons are less, suppose only 2 electrons are there, then they occupy only one shell. And in the multi-electron atom, if they are having more electrons, they are occupying different shell. That is the SPDF, the lowest total electronic energy corresponding to the most stable, that is the ground state of an atom. The orbital wise distribution of electrons in the ground state can be understood from what is called the Apow principle. So, this is the very important principle how to write the electronic configuration, that is the Apow principle. You have to write the electronic configuration in ground state of an atom, and that time lowest total electronic energy corresponding to the most stable. So, we will see what is the Apow principle. Aufbau is a German word meaning building up. The building up of orbital means filling up of orbitals with electrons in ground state of an atom. The Aufbau principle is based on increasing order of energies of orbitals, second Pauli's exclusion principle, and third Hertz's rule of maximum multiplicity. So all these, that is the Pauli's exclusion principle, Hertz's rule of maximum multiplicity, Aufbau principle, they are the basic rule for writing the electronic configuration. See, in this diagram we will see the increasing order of orbital energy is giving. See, when you are filling the electrons in orbit, so 1s orbital is first filled, then 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s, 4f, 5d, 6p, 7s, 5f, 6d, 7p, 6f. So, in this way the electrons are filled. And how to draw this diagram, how to practice this diagram? So, first you have to first see, there it is written total 7 circles are drawn with first 1s, 2s, 3s, 4s, 5s, 6s and 7s. So, first you will draw the 7 circles and write in that 1s, 2s and up to 7s. Then second is start from the second one. You have to draw the 6th circle. In 6th circle you are starting with the 2p, 3p, 4p, 5p, 6p and 7p. So after this one more less and you have to draw only the 4 circles, and in that you have to write 3d, 4d, 5d and 6d, and then you have to draw only 3 circles 4f, 5f, 6f. So first 7 circles containing 1s to 7s. Second set of circle start from 2p to 7p. Then third set of circle starting from 3d to 6d, and the last circle 3 circles having 4f, 5f and 6f. So first you have to practice this diagram, because while electron filling in different orbit, this diagram you should know, and accordingly you have to filling the electrons in each orbit. The increasing order of energies of orbitals. As seen in the section 4.74, the increasing order of energies of orbital is decided by the n plus L value, that is principal quantum number plus azimuthal quantum number. Electrons in the ground state atoms are filled in the orbitals in an increasing order of energy. The diagram shows a useful method to remember this increasing order of orbital energy. So in the last diagram I have already explained you how to draw the circles and how to write in that 1s, 2s up to this. So this diagram explains the filling of electron according to the increasing order of energy level. Then we will see what is the Pauli's exclusion principle. The capacity of an orbital to accommodate electron is decided by Pauli's exclusion principle. So you know the orbitals are s, p, d and f. The capacity of s orbital is only 2 electrons. Then capacity of p orbitals to accommodate the electrons is 6, d 10 and f you can accommodate 14 electrons So the capacity of an orbital to accommodate electrons is decided by Pauli's exclusion principle. Wolfgang Pauli in 1926 reorganized that no two electrons in an atom can have same set of or-fold quantum numbers. What it means, suppose in particular atom there are two electrons and the first electron is having the value of n, l, m and s, that is the principal quantum number, azimuthal quantum number, magnetic quantum number and spin quantum number, and the second electron is having also the same values. So no two electrons in an atom have the same set of four quantum numbers. Both the two electrons should have the different values of this four quantum number. Another way to state this principle is only two electrons can occupy the same orbital and they must have opposite spin. So in any orbital there it should occupy only two electrons and that electron should have opposite spin. One means one in angular direction, then second is in anti-parallel, parallel and anti-parallel direction. One is in upward position and second is in downward position. Pauli's exclusion principle implies that for an electron belonging to the same orbital, the spin quantum number must be different. Because spin quantum number must be different means what? Spin should be opposite. If one is moving in parallel direction, then second should move in the anti-parallel direction. Clockwise and anti-clockwise, you can remember like this. One electron should in clockwise, then second should be in anti-clockwise. The difference is the other three quantum numbers n, l, m are same. Only their spin quantum number should be different while other principal, azimuthal and magnetic may be same. There are only two values that magnetic quantum number can reach, having the plus half or minus half. So spin quantum number of electron is either plus half or minus half, means either in clockwise direction or anti-clockwise direction. An orbital thus can accommodate only two electrons with opposite spin, so that fourth quantum number is different for two occupying electron. These two electrons with opposite spin occupy the same orbital are called electron pair. So when you using the word electron pair, then you always remember that one should be in clockwise and other should be anti-clockwise. Both clockwise means both parallel electrons cannot accommodate in one orbital. Always there should be one parallel and second anti-parallel, or one clockwise and other anti-clockwise. So Pauli's exclusion principle tells us that the electron accommodated in the orbitals have opposite spin. Their spin quantum number should be different while principal, azimuthal and magnetic quantum number may be same, but their spin quantum number should always be different. One is having plus half and other is having minus half, means magnitude is same but direction is different. One is having the clockwise direction and second is having the anti-clockwise direction. This principle is illustrated with helium atom having the atomic number 2. Its electronic configuration is 1s2. See how it is shown in the block diagram. There is a one rectangular block is drawn and in that one arrow is in upward position and second arrow is in downward position. And two electrons are in 1s orbital. The two non-identical combination of four quantum number of both the electrons in helium are given in the table. See, first electron, see in helium there are two electrons. First electron n is having the value 1, that is the principal quantum number is having the value 1. Second L0 means azimuthal quantum number is 0, magnetic quantum number is also 0, but spin quantum number is plus half. So what is the set values? 1, 0, 0 and plus half. Second electron is having the same value for L, M and magnetic quantum number, but only spin quantum number is having the value minus half. So set is 1, 0, 0 and minus half. So this implies that in any atom, if there are 2 electrons, they may have value of n, l, m same, but spin quantum number should be always different, means either plus half or minus half. It implies that 2 electrons in the same atom have always different set of quantum number. That means the set of n, l, m, f is the same and ms is different, means spin quantum number is different, but remaining 3 quantum number may be same. So all of you understood this Pauli's exclusion principle. You have to remember that 2 electrons should have all the 3 values of quantum number same, only the magnetic quantum number, only the spin quantum number should be different. Since an orbital can accommodate up to 2 electrons only, the capacity of a shell with principal quantum number n to accommodate the electron is given by the formula 2n square. See how this formula is used. See, in the first orbit, n is having the value 1. So 2n square means 2 into 1 square, that is 2. So in the first orbit, accommodation of electron takes place, only 2 electrons can accommodate. In the second, n is having the value 2. So 2 into 2 square, that is 8. So in second orbit, electrons accommodated are 8. Then in third, 2 into 3 square, that is 18 electrons can accommodate in third shell. So like this, using this formula 2n square, you can fill the electrons in different orbit. So first we have completed the Pauli's exclusion above principle. In above principle, they have given the energy levels, how the electrons are filled up in energy level. Second, that is Pauli's exclusion principle. Now we'll see the Hertz rule of maximum multiplicity. Filling of electrons in the orbitals belonging to the same subshell. Orbitals of equal energy or degenerate orbital follow the Hertz rule of maximum multiplicity. As per this rule, pairing of electrons in the orbitals belonging to the same subshell does not occur unless each orbital belonging to that subshell has got 1 electron each. What is this Hertz rule of maximum multiplicity? Means when you are filling the electrons, suppose there are p orbital is there, and in the p orbital 6 electrons can accommodate. So there are 3 orbitals px, py and pz. So first you have to fill each electron in each compartment, that is 1 electron, and then you have to pair the electrons. It should not happen that pairing should be done first. So first each orbital is getting 1 electron and then you have to pair. Consider for example filling of p subshell. The p subshell has 3 degenerate orbitals. Here pairing of electrons starts when 4th electron enters. Means in 3 compartment, 3 degenerate orbital, 1 electron is filled and the 4th electron will be paired. The electronic configuration of 4 electrons occupying p orbital will be, in the first it is given is right and not the second one. In second one what happened? Both the pairing takes place in first and second and third is empty. It should not happen. So in the first you have to give 1 electron to each degenerate orbit and then you have to pair. So this is the first one is the correct and the second one is wrong method to fill the electron. It is observed that half filled and fully filled set of degenerate orbital has extra stability. This is very important. Half filled and full filled set of degenerate orbital has extra stability. Electronic configuration of atoms and its representation. Electronic configuration of an atom is the distribution of its electron in orbitals. The electronic configuration can be written by applying the above principle. There are two methods of representing electronic configuration. Orbital notation NSA, NPB and NDK, and orbital diagram. So first you have to write the orbital notation and then orbital diagram. See, so we will see first representation of electronic configuration of first hydrogen. Hydrogen having the atomic number 1, so its orbital notation is 1s1. So in one block, one degenerate orbital, you have to draw only one electron with upper direction. Helium He2 1s2. So in 1s orbital you have to show the two electrons with opposite spin. Lithium having the electronic configuration 1s2 2s1. So 1s2 means first you have to show the 1s with both the electrons in parallel and anti-parallel direction, and in 2s you have to show only the one electron in upward direction. Then beryllium 1s2 2s2, both should get paired. Then fluorine 9 atomic number 1s2 2s2 2p5. See 1s2 2s2 2p5, you have to draw the T blocks. First is px, second is py and pz. 5 electrons you have to fill. So first orbit 2, second py2, and in the third pz you have to fill 1 electron. Condensed orbital notation of electronic configuration. The orbital notation of electronic configuration of an element with high atomic number comprise a long train of symbol of orbital with an increasing order of energy. It can be condensed by dividing it into two parts. Electronic configuration of preceding inert gas is a part of electronic configuration of any element. In the condensed orbital notation, it is implied that writing symbol of that inert gas in a square bracket, it is the core part of the electronic configuration of that element. The outer electronic configuration is specific to a particular element and is written immediately after the bracket. So first you have to write the electronic configuration of inert gas and then outer electronic configuration. For example, orbital notation of potassium. Potassium having the atomic number 19. Its electronic configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. Its core part in electronic configuration of the preceding inert gas is argon. 1s2, 2s2, 2p6, 3s2, 3p6. This is the electronic configuration of argon, while 4s1 is outer part. So how to write the condensed notation? First in square bracket you have to write the argon, means first follow the electronic configuration of argon, and then 4s1 means outer electronic configuration. So table displays the detailed and condensed orbital notation of electronic configuration of various elements with atomic number from 1 to 30. There is table is given, and in that table all the elements having the atomic number 1 to 30, their electronic configuration is written. Electronic configuration of copper and chromium. Copper and chromium are the different cases. Atomic number of chromium is 24. So its expected electronic configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d4. In this case, 3d is not half filled. See, when 3d get half filled, when it's having the 5 electrons, hence it has less stability. So inter-electronic repulsion makes one 4s electron enter into one empty 3 orbital. So one electron from 4s orbital jumps into 3d orbital, so it becomes 3d5. So due to inter-electronic repulsion makes one 4s electron enter into one empty 3d orbital. Thereby both 4s and 3d orbitals become half filled, so that chromium atom acquire extra stability. Why chromium is having the extra stability? Because its outer 3d orbital is half filled. Its electronic configuration now it's become 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, 3d5. See the difference between the actually observed and expected. One electron from 4s orbital is jump into the 3d orbital and it's become half filled. And you know that half filled orbital is having extra stability. So this happened with chromium and copper. Now you will see the copper. Atomic number of copper is 29. The expected electronic configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d9. Here 3d orbital is neither half filled nor full filled. So due to inter-electronic repulsion forces, one electron from 4s orbital enter into the 3d orbital and make it completely filled. Completely filled means what? It will become 3d10 and 4s become 4s1. Hence, copper atom acquires extra stability. Now electronic configuration of copper is 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, 3d10. So this is the anomalous behavior of chromium and copper due to having the extra stability. In chromium their d orbital is half filled and in copper the d orbital is full filled by jumping of electron from 4s to 3d. Isoelectronic species. Atoms and ions having same number of electrons are called isoelectronic. The electronic configuration of isoelectronic species is the same. Consider K plus formed by removal of one electron from K atom, which has 19 electrons, therefore K plus having 18 electrons. When any element is getting the positive charge, always there is a loss of electron. So K plus means potassium is losing its one electron. So there are only now 18 electrons are remain. So species like argon, calcium 2 plus containing 18 electrons are called isoelectronic with K plus. So electronic configuration of all these species with 18 electrons, that is 1s2, 2s2, 2p6, 3s2, 3p6. So this is the isoelectronic species concept. Now there is a table is given and in that table electronic configuration of first 30 elements is given. Hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, argon, potassium, calcium, scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper and zinc. So you try to write the electronic configuration of these elements according to their atomic number, according to using the above principle, Pauli's exclusion principle, Hund's rule of maximum multiplicity, and write also the condensed electronic configuration. So you can practice according to this chart is given. So today we have completed this chapter, that is the structure of atom. So in the next lecture we will start with the another chapter. So please try to write the electronic configuration, make the practice of writing the electronic configuration of different elements with a different atomic number. Okay, thank you.